Cool. Thank you, Alan. And thank you, everyone, for coming here. I'm happy to share with you today our recent work related to explaining the anomalies in financial tabular data. And a couple of words about myself itself. I'm coming from the computer science world and currently a PhD student at the University of St. Gallen here in Switzerland. At the same time, I work full-time employed at the German National Bank or the Deutsche Bundesbank, which is a financial regulator in Germany. And my main focus is basically lies at the intersection of deep generative model learning and finance domain. And so this is basically where my focus of my PhD is around. And that's why I would like also today advertise you a couple of papers that we did recently related to the explainable AI area. The first one is a very nice paper where we joined autoencoder neural networks with Shapley values. This was done together with the nice colleagues of me, Ricardo Müller, Marco Schrey, and Professor Bort. But I would like to focus today's talk on the second paper, which is related to explaining the anomalies using the denoising autoencoder on neural nets, with the focus on financial tabular data. And I will start my motivation remembering you or giving a bit of recall on how impactful the financial frauds on economics of different countries, but also on companies or even individuals. We hear it quite often in news, and that's why as a regulators it's always important not only to define a certain policy levels, but also to look at the quality of data that is being shared among financial institutions. So sharing of high quality financial data is one of the key important factors for stable economic activity. And the way how it's happening usually in Europe, in USA, or in many other countries is the following. The financial entities in any country, like banks, for example, or some financial funds, they share on a regular basis their financial activities. So the data about their financial activities, like credits, for example, and deposits and so on. And this statistics is being shared on a daily basis, on a monthly basis, or even on a quarterly basis with regulators. And it usually consists of these three steps. Yeah, first is the data collection. This is when the data is being delivered to the regulator. Then in the second step, there is a data screening process or the error detection process, because as I said, the quality of the data is very, very important, as this influence later on how the economists would develop their models and what kind of interest rates you would get tomorrow. That's why the financial stability here actually plays a big role. And that's why the second step is indeed very, very important. And there are a lot of domain experts who are sitting and basically double-checking sometimes certain transactions. And if there is a certain consider or certain issues that are happened here, a certain error correction inquiry is being sent back to a bank or the financial institution for corrections. And this cycle is being repeated over and over again until all the concerns are resolved. And usually there are two big types of issues that arise, or two big types of concerns that are detected. The first one is the typos, regular typos or mistakes that are delivered, where the person who is sharing the data maybe has made some typo, the commas or some wrong values. And these are reporting errors, and they're easily detected by rule-based systems. However, the second type are the anomalies, which are related to market fluctuations, like during the financial crises, for example, or certain stress scenarios where the economy of the country is under certain stress conditions. These market fluctuations can be reflected in the anomalies that are reported. And such anomalies could be detected using the pattern-based systems, obviously based on historical data that was previously delivered. And as you probably know, there are a bunch of anomaly detection techniques that are developed today, and it's quite popular there are a lot of popular anomaly detection techniques that exist today and can be deployed, and those anomalies can be easily detected, right? So if we take an example here, there is a tabular data that was delivered to a regulatory institution. The traditional anomaly detection technique would yield a binary outcome for each individual transaction, whether it's an anomaly or not, and add maybe a certain confidence level. How likely is this an anomaly? However, the problem is that it's just a single scalar which answer only a single question, which samples are the anomalies. But it doesn't answer the question why it is an anomaly and why the model has flagged it as an anomaly. In addition, it doesn't give the information about what should have been reported instead. So what the model is actually expecting to be delivered so that it's not an anomaly anymore. And that's why our motivation was here is to develop an explainable anomaly detection tool that would answer these exact questions. So in addition to flagging the samples that are anomalous, it would allow to answer the question why it is an anomaly by flagging individual attributes that might potentially contain errors or might potentially be irregular. So for example, the transaction number 4, the attributes x1, x4, and 5, this combination is very unusual for the model, and it will be flagged as irregular. And this would answer basically the question why it is an anomaly. And we call it cell error detection. In addition to this, the model should provide so-called expected values, where the model says, okay, at this particular field, at this particular cell, I am expecting this particular value. In this case, if this value would be delivered, then I wouldn't kind of label this as an anomaly. You can think of it also as a counterfactual explanations probably, because this is kind of what-if scenario in this case. Right? And that's why our research question was the following. Can traditional anomaly detection techniques be extended to explainable anomaly detection techniques? And if yes, can they be used for financial tabular data of the mixed type? And the idea was to use the cell-wise anomaly detection. We utilized the denoising autoencoder architecture, and the hypothesis was to utilize this attribute cell-wise detection of errors. So we're not looking at the individual, the complete reconstruction error of a particular sample, but we kind of drill it down to individual fields or individual attributes. And this type of cell-wise anomaly detection would explain the cause of an anomaly to a person who is working with the data. And for that, we started, as I said, with autoencoder neural network. For those of you who is not familiar with autoencoder neural network, it's a special type of neural net that which's goal is to reproduce its input. The model consists of two neural networks. The first neural network, the encoder neural network, encodes or compresses the input data to a low-dimensional space, and the decoder neural network reconstructs the data to original dimension. And the difference then between the reconstruction and the input is computed, and this difference, or this scalar, is usually is used to reflect the anomalies, to reflect the quality of the anomaly, whether the sample is anomalous and how it's anomalous. Now, for financial tabular data, and in particular the denoising version of the autoencoder is slightly different. It's an extension of the autoencoder neural network, where the model has an additional corruption step before it's fed to the model, and this corruption phase is simply contains of adding the noise to the data. Yeah, so you're basically randomly selecting some features and just adding the noise to these features. There are many ways of how you can do it on tabular data, because it consists of mixed types of data. Afterwards, once you did the corruption, basically you fit the corrupted data into the model, into the autoencoder, and the goal of the autoencoder in this case is to reconstruct the clean data. And once the model is trained like this in the following setup, the model is able to learn the type of noise that was added during the corruption phase. And this idea helps the model to realize where exactly, since we are doing the cell-wise detection, it allows to identify where exactly the noise was injected. And once, as I said, once the model is trained on the training data, in the inference phase, you can feed the new data, compute the reconstruction of each attribute, and then look which attributes or which values in the attributes were not reconstructed. And you flag this as the cells or the values of these cells that are potentially contain an error or potentially irregular, given the historical data. In addition, when you look at the reconstruction of this field, you take this value and you can use it as the sort of expected value. So this is basically what we use for computing the expected values for the model. So this is basically what the model expects to be delivered in this field, which answers basically the third question that we had, right? Our experimental setup was the following. We took the three open source data sets, tabular data sets with a mixed type, and one proprietary data set. Categoricals, for categorical attributes, we used the popular one, hot encoding transformation, and for numericals, we stand for the standard scalar. And we trained them with the model with the following hyperparameters. We also defined a certain metrics to measure the quality of the detection rate from the different perspectives. And we defined these three metrics to answer each question that we had in the very beginning. Yeah, which samples are anomalous, why it is an anomalous, and what should have been reported. So these three metrics we used to measure the quality of the data or quality of the model from different perspectives. What is interesting is also we noticed that specifically for denoising autoencoder, it's very important that the amount of noise and the type of noise that you inject during the training plays a big role. Because if you inject too much noise, then the model focuses entirely on noise removal step. And that's why it kind of not focuses on the clean data anymore, because you're adding just too much noise, and it kind of shifts its main learning trajectory towards the noise removal process. But you still want, ideally in practice, you still want to train, or you still want to reconstruct your clean data pretty well, because usually the anomalies, they are not majority, there's just maybe less than 3% of your data. And if you add too less noise, it decreases the noise removal process. So the model is able to only reconstruct the clean data, but then forgets the noise removal process, and your explainable criteria just vanishes. And that's why we saw that depending on the data set and the data set structure, it's quite important how much noise you're adding. And we decided to add this kind of intelligent loss, when the model will be able to automatically identify how much noise needs to be added at for the particular data set. Also, this is the results of the experimental. These are the experimental results across 4 data sets and 5 different benchmarks. And we saw that the denoising autoencoder performs quite well here. We also noticed that a very big role plays the real-world noise, since we have worked with real-world data here, with the proprietary data, and we saw that if you have a real-world noise or real-world errors, then it boosts the performance quite a lot. And this is the kind of qualitative overview of how this anomaly explainer would look like for a domain expert who would screen the data, for example. And if there is a new data arrived and a new sample that needs to be screened, for example, the model would yield in the following way. First of all, it would flag the certain attributes that contain potential errors, and then it would yield also certain confidence levels of how likely there is an error in this field. But also it would provide, as I said, the expected values of for each individual entry, for each individual sample cell. And again, this is something similar to the counterfactual explanations, like answering the question, what if the value would be reported. And in addition to this, we also look at we provide also the 5 closest neighbors. This is quite nicely, this was quite nicely possible using the autoencoder neural network, because you can extract in the latent space this compact representation of the data, and you can easily and fast find the closest neighbors. This was very important to have it also for the domain expert who would like to look at similar transactions that were reported previously, maybe, or in the similar period. Speaking about the latent representation or compact representation of the data, the autoencoder provides also this dimensionality reduction. You can also use it as a dimensionality reduction technique, right? And what is nice was also is to use it for the domain expert as the qualitative tool, which would also add additional layer of explainability for a domain expert, saying, okay, and there is a particular group of transactions that are joined together, and they are most likely probably have something unusual in their case, and the domain expert can simply sample from this particular region and kind of what we call walk in the data and traverse in the data and very fast identify what was wrong about it and what are the similar transactions that led to this problem. If you compare such compact representation of denoising autoencoder on the left side and then the vanilla autoencoder on the right-hand side, we saw also that the denoising autoencoder, which was much better in this case, since it was able to combine the anomalous observations into a single group, which was much helpful for the domain expert as a visual explainability criteria. So this is everything that I wanted to share with you. I hope I'm on time, and I'm happy to take any questions, and thank you, everyone.
Do we need to call for questions?
Thank you for your talk. I had a question about the noise you added. So you told us you kind of make sure it's not too much, not too little. But would you also try to control what kind of noise you add, such that it actually represents maybe the most frequent kind of noise that you would actually see in the real world?
Mm-hmm. Yeah, that's indeed a great question. As I mentioned before, the amount of noise plays the big role, but also the type of noise is essential. We used in our experiments, we used the popular type of noises. So for the numerical attributes, for example, the Gaussian noise, and for the categorical attributes, we flipped the categories just randomly. But we indeed noticed that if you have a real world noise, meaning that if you have a certain data set where you know that on this particular transactions they contain errors, this is significantly different from the artificial noise that you generate. And once the model is able to be trained on the real world noise, this boosts the quality of the model significantly. We saw it on our training set with our proprietary data set. We did 2 different experiments. We trained the model with artificial noise. It gave good performance, but then once we gave the model also the real world noise, once it was able to see how the real world noise looked like, the quality dramatically went up. So this is indeed very, very important.
Thank you.
Any other question? Okay, so let's thank the speaker again.
Thank you.